record. Okay. Yeah. Do you need a bit review about what the problem is? Right. So we are cutting the rod into different into segments of different lengths as our wish, and then we want to maximize the total revenue because the rod of different lengths sell at different prices given this table. Okay, so this is some known information. That will be part of the input to the algorithm, and we have the flexibility we have the freedom to choose whichever place we want to cut. Okay, and also last time we have come up with the optimal structure, which is that the problem, the solution to the original problem actually comprises the solution to the subproblems. Okay, by finding the optimal solutions, the optimal revenues for the smaller problems, we're able to obtain the solutions to the bigger problems, to the original problems. All right, so a slightly simplified version is like this. So we assume that given the cuts, we don't further cut into the left half. Okay, we just cut into the next half, the next the right parts. Yeah. Okay. And given this the optimal structure, we actually implement something that's quite that relies on the simple recursion recursive calls. Okay, so it's like we recursively call this cut rod whenever we have a cut, right? We have a cut at the place I, right? So I could be any locations between 1 and n. Okay, whenever we had a cut, we will compute this price, which is sell the right part directly and to further cut the right part, right? So now the right part has a length input n minus I because the length I is being sold, right? So we basically use this summation as one option to compare with the Q, okay? So Q will be the result of comparing all I's, then the Q will be returned. Okay, but we find that this is a very inefficient algorithm, right? Because whenever we had a problem, we need to call the function cut rod recursively, right? So it's the function itself. And this recursive call actually don't care about, actually doesn't consider the possibility that the problem has been already solved. Okay, so it's pretty much like the inefficient Fibonacci problem as the first example. Right, the same problems got solved over and over again, and the recursive calls, if we draw it in the tree, it's basically a lot of repeated nodes. A lot of nodes with repeated values. Okay, so if we look at if we have the recurrence equation expressed like this, it's basically the exponential function 2 to the power of n, which is extremely inefficient algorithm. So in the dynamic programming, the first top-down dynamic programming approach for the rod cuts, we slightly modify the cut rod function by basically, right, we define this minimalized cut rod function. We first add 2 lines of code to check. Okay, so this is to check whether the same function, whether the subproblems has already been solved. So if so, we will just return the results because that is a reasonable way to go, right? Whenever we have the records, right? Why not just we return it? We just simply don't need to solve it again. Okay. So if not, then we just solve it in the usual way. Okay. So this part is a recursive call function to the function itself. So this part is not that different from the naive recursive solution. Remember, in the naive recursive solution, it's just a different function name. We just have cut rod here and cut rod here, right? Now we just change names, but now the difference is that we have the R as inputs. Okay, the R as additional inputs because it saves the historical information. Okay, and another difference is the line 8 here. Whenever we have the Q solved, we need to store it into R. Okay, so this R is where we got the arguments here. The R is one of the third argument, so we can update the values in R. Okay, so you can think of the R as the array R as a kind of a lookup table. Okay, kind of a lookup table that we can modify whenever we found necessary. Okay, so the Q will be stored into R before we return it. Okay, so with two critical changes to the algorithm, we are actually implementing this. We actually improve the performance of this cut rod quite significantly. So yeah, we haven't analyzed the running time of it. So we're gonna analyze it after we have introduced the bottom up method today. All right, so first let's still go through another example. Okay, so this is the example we have already gone through using inputs size equals 2. So I guess if we have input equals 3, how we save the time by avoiding solving same problems is more significant. Okay, let's see. The initial call to the memorized cut rod auxiliation procedure will be like this. Now the input will be 3, right? So the I basically iterates from 1 to 3. So in the first iteration, I equals 1. So we will still differentiate the colors of Qs. Okay, in this level, in the original call, in the top level, the Q will be in the black color. Okay, so Q will be compared with the original infinity with the P1 plus the recursive call on n equals 2. All right, and we need to step down into this recursive call. Let's make it color the blue color. Okay, and then within the blue recursive call, there will be a blue I, right? This blue I iterates over 1 to 2. Then in the first iteration, marked by the blue color, the blue Q will be compared with this third recursive call with n equals 1 as input. Okay, and we will find that the value of it is 2. And in the second iteration, when I equals 2, the Q will be compared to the third recursive call, which is on 0, n equals 0, right? So we didn't step down. Actually, we didn't step down into this recursive call, okay? Because we have solved that before. So the first Q returned from the first iteration of the black Q, it'll be 6, right? But we have a second iteration for the black I and the black Q, right? And remember here we have so we should notice here, right? We have a recursive call on n equals 1, and this is exactly what we have solved before, right? So this time we will directly return the values, okay? Return the values for this solution. But we don't need to step down to the recursive calls. And in the third iteration here, the memoized cut will be called on top of n equals 0. And this time, this brown part is already computed at this step. So we just refer to the results of the previous call. We don't need to go down to the recursions. So anyway, after all these steps are done, the final revenue will be returned within this area R. Okay. All right. Okay, so basically these will contain everything we need for the solutions. So it's especially because the input is 3. So this is elements. This R of 3 is the one we care about mostly, right? We care about the revenue for cutting a rod of length 3. But we should notice that in order to get the last elements here, we need to first solve all the elements in sequential order, right? We solved R0 first, and R1 and R2, and eventually R3. Okay, so this actually reveals some thoughts about some ideas that we can actually solve the problem in a bottom-up style, right? Because the larger problems depend on the smaller problems, and the smaller problems depends on even smaller problems. So why not we start from the smallest case, right? We just solve the smallest case and then eventually solve all the problems. That is the bottom-up dynamic programming approach we will look at today. Okay. So we can actually basically solve the subproblems in increasing order of the size, in size order. Okay. And so when we are solving a particular subproblems, we have already solved all the smaller subproblems that its solution depends upon. Okay, so let's look at this solution. Now it's called a bottom-up cut rod. Okay, we don't need an auxiliary function now. We just basically define one procedure, like straight away. Okay, and we will initialize the R this time inside the procedure. It's not like provided as an external argument here. Okay, and also like the second line of code is the initialization necessary, right? Because we want to define the revenue for. So this is theoretically, in theory, this is the smallest subproblem. Right, the smallest subproblem is the length 0 case. So we will just let it be 0. Okay, and next we have a for loop. Right, we have a for loop. Actually, it's 2 for loops. So nested for loops. The outer for loop, it iterates from 1 to n. Right, that is the order of solving all the subproblems. Okay, we need to solve the subproblem of size j in such an order, right, from 1 to n. That makes sure that we solve the smallest subproblem first. Okay, so the j is not from 0 because the 0 is already solved here, right? The 0 is a straightforward solution, so we just start from size 1. Okay. Then how do we solve the subproblem of size j, right? Then it goes back to the original, optimal structure of the problem, right? Given a rod of length j, okay, now we know the length is j, right? How we solve this problem should still follow the same strategy. We will let a second counter I that iterates from 1 to j, right? Because now j is the input size. We will let I to slide through the length j rod, right? We let I equals 1, 2, until j, okay? And upon each cut, we will need to compare the resulting revenue, which is PI, okay? Solving the left parts, directly selling the left parts, and the optimal solution on the right, which is the revenue of j minus I, right? Because if I choose to cut here, then the remaining length would be j minus I, right? So the Q will be solved in a similar style. Well, it will be compared with the previous value and try to find the max one, and the results will be saved to R of j, right? When we have the inner for loop terminated, okay, and then the result will be returned. Okay, so one thing we can find that, okay, I see a question now.
Professor, I have a quick question.
Yes.
So, I was just confused. So, R from 0 to n, does it get initialized? Because when we go in the first loop, R of j minus 1, are they all defined?
Yeah, that's a very good point. So the R0 will be defined, and the j will start from 1. Let's consider j equals 1. In the iteration of j equals 1, then I will be 1 to 1. So there's only one value for I. So the only value for this index will be 1 minus 1, will be 0. And 0 is already defined. Okay, and then we will know that the R1 will be stored by the Q, by whatever Q return. Okay, so R1 will be updated. So after the j equals 1 is done, let's look at the second solution, the second iteration, which is j equals 2. Then when j equals 2, in the case of j equals 2, we will have I iterates from 1 to 2. Right? And for I equals 1, j minus 1 will be 1. When I equals 2, j minus I would be 0. Okay, you see, the point is that when we try to solve the problem of size j, the subproblem need to be solved is always smaller than these two. Right? When we try to solve j equals 1, it only depends on r of 0. When we solve j equals 2, it only depends on r of 1 and r of 0. It only depends on the solutions to the smaller problems. We don't depend on larger problems. So that is okay. When we have j equals 3, we need to depend on r of 2 and r of 1 and r of 0, right? But it's already, the r of 2 is already solved in the previous iteration for j, okay? With the help of the line 7, we will save the results for rj before the next iteration for j starts.
Okay, that makes sense.
Yeah,
Thank you.
yeah. So this is actually the essence of this bottom-up method. We organize the order of solving all the subproblems in a smart way that we always solve the smaller problems first, so that in the later stage, when we solve the bigger problems, we have all the dependencies already fixed. Okay, because the bigger ones depend on the smaller ones. Okay. Yeah, so in that sense, the order of the for loops in the bottom-up dynamic programming approach actually matters. That's actually a very critical factor. Okay. So yeah, you see the difference is that compared with the top-down method, the difference is that we like don't use the recursive cost for this line, for this part. We just use a lookup table. We just use a lookup array. Because when we look it up, it's always solved. It's already always there. Okay. All right. And the line 7 actually is also critical. It saves the results to the array R. So we have a example here. Let's go through this quickly. Right. So let's just assume that everything is initialized such a way. So we put all the zeros here, but it doesn't matter what initially those values are. Okay, so it's just for convenience. We just make them all zero. So the J will start from 1. Right? Remember, so this is an example that I showed on the previous slide. And I will be only one value, which is 1. So Q will be the comparison between P1 plus R0, which is 1. Okay, and that 1 will be saved to R1. So this will update those value, this value, right? It's no longer 0 now after this iteration. All right, you see the difference here? We have the R1 updated. It's no longer 0, okay, after J equals 1 is done. So in the next iteration, when J equals 2, I has 2 values, I equals 1, right? We need to compare it with R1, right? Which we directly copied from the cell here. And when I equals 2, it's R0 that needs to be used, okay? And this, after this iteration is done, R2 is solved and it's saved to this cell. So for the next iteration, R2 is also has a valid value. So in the next iteration, J equals 3, I iterates from 1, 2, and 3. We can always have the values for R available, and R3 is also saved eventually, and that is the results we are looking for here. All right, that is the bottom-up style.
So just another quick question.
Mm-hmm.
So I understand how the procedure works. So at the end of the algorithm, we have to return what lengths we need to buy to get the maximum revenue, correct?
Yeah.
So how would we do that here? Like, once we generate R?
Yeah, that's also a very good question. So far, we just record everything. We just record the revenue, but we didn't mark the steps. We didn't mark the place that we place each cut, right? So in order to return that, we will need to use, this algorithm is not sufficient. We need to use a second array, okay? I think I have a slide for that. So we need to use a solution array other than the revenue array to store the i's. Whenever we have a cut, we need to mark those i's. Okay. Let's I will answer that question when we encounter that, when we go into that slide. Okay. All right. So when we analyze the running time for the dynamic programmings, it's usually easier to understand, to analyze the bottom-up implementation, because the top-down method involves some recursive calls, and it's not that straightforward to determine the recurrence equations for the recursive calls. So let's focus on the bottom-up cut rod problem. And actually, the running time is quite straightforward. It's bounded by this quadratic function because it's the double for loops, the nested for loops, right? When we have one for loop inside the other for loop. So actually the number of iterations for the inner loop, it's actually they actually form an arithmetic series, and the summation of an arithmetic series, as you already know, it's a very common quadratic function. Okay, so in order to strictly analyze the top-down method, we need some advanced technique called aggregate analysis. But in this course, we're not going to cover that method. Okay. All right. So now let's consider the sequences of how subproblems are solved in a dynamic programming problem, because this subproblem graph is similar to the recursive tree that we draw for the pure recursive solutions. So if we look at, we use those nodes to represent the values of the, to represent the size of the problem, and those connections to represent the dependencies. The connection for R4 to 2 to 3 to 1 0, it basically means that in order to solve this problem, we need to depend on all the other nodes. And R3 has a connection to 2 1 0. It means that it depends on the subproblems of 2 1 and 0. Okay, so this is similar to a tree, right? But it's not a tree-like, but it's actually something that has similar function to a recursive tree that describes the dependencies of subproblems. Okay, the difference if we compare this subproblem graph with the recursive trees several slides ago, we actually can find there's no repeated nodes in this graph, and only each subproblem is only solved for just once, right? If you remember this curve, this tree on the left, this is something we draw when we define this naive cut rod function, right? We have zeros, a bunch of zeros, right? This a bunch of zeros, all the leaf nodes, we can actually merge them, right? If you imagine it's in your mind that we merge all the zeros, it actually we can convert the tree plot to the subgraph on the right by merging all the nodes with the same values. Okay. So actually, Fibonacci problem can also be described by the subproblem node. Okay, from like the bigger problems depends on the previous two subproblems. Okay, so there's no connections in the Fibonacci problem. That's the 3 only depends on 2 and 1, right? And the 4 only depends on 2 and 3. So there's no such a connection from 4 to 1, right? So this is the difference. So this is actually something very unique to each problem, right? For the nature of the problem, we should we should draw different the subproblems of different structure. Okay. Yeah, I see a comment that it's not truly efficient. Yes. So because the problem size, the problem space is very large for solving the rod cutting problem, is actually a lot of combinations we should try. So it's not actually the flaw of the algorithm, but it's determined by the nature of the problem. Okay. So now we get to the points of the question of if we want the actual solutions, but not just the revenues, we actually modify the algorithm so that it does not only record the optimal value, but also the choice that led to the optimal value. Okay, so we can basically, in the case of the bottom-up method, okay, it's extended. Okay, so it's now will initialize this S array, and S is for solution. So this S array will be used to store all the i's that made the cuts. Okay. Okay, so now we can basically rewrite the function. Okay. Oh, so a little bit difference is that here within the for loop, okay, there used to be in a non-extended version, in the original version, we have a max function. Okay, but now in order to show that in order to better write the code, we should not use that max function, because we need a control statements by comparing the value of Q with the new cut, which is at the place of I. Okay, so if the new cut is better than the older one, than the previous one, we need to not just to record the revenue to Q, but also remember the solution to S of J. Okay, because since the S of J is the solution for it is to actually remembers the optimal cut, the first cut of the optimal solution. Okay, so let's pay attention to the range. The J ranges from 1 to n. So the S also ranges from 1 to n. Okay, so S of J actually tells that in order to get the optimal solution for the subproblem of size J, then where we need to place the first cut. Okay, so that is the information we need. Okay, and you may ask that, what about the remaining cuts? Okay, so in order to solve the subproblem of size J, where is the first cut, right? That is I, right? Let's assume that this I is saved in S of J. Okay, then what about the second cut? Then the second cut can be retrieved like recursively, right? Because the second subproblem would be J minus I, right? So we need to refer to the elements of S, Sj minus I, right? So let's go to the next slide to see how the subproblem, how this new extended version of bottom-up cut rod can return. Okay. Now, assume that it returns the results like this. We have now R and the S with all elements filled out by the algorithm, and say this value actually means that in order to get the optimal value from a rod of size 9, then the first cut should be of size 3. That's the meaning for each element in S. Okay, so like the remainder part is of length 9 minus 3 equals 6, right? So we need to simply refer to S of 6, and in this case, it returns the elements. It returns the value 6, right? Which means that we don't cut the side, we don't cut the rod of length 6 at all, right? All right. So in order to output the complete list of the cut sizes, then we can define a function on top of the results. Okay, we simply on top of the results of this S, we can print the elements in such an order. Okay, and by decreasing this n. Okay, so it basically if we let 9 be the inputs, then we will print S9 equals 3, S6 equals 6, which will be the solution for this rod cutting problem. All right, and so far I think we are pretty much done with the rod cutting problem. And before we go to the next example, let's summarize a little bit about dynamic programming. Like in what cases we can use dynamic programming to solve the subproblems. So actually observation of the problem is very important. We need to find whether we need to determine whether there is a optimal structure in the problem. So it means that the optimal solution to the problem actually contains the optimal solution to subproblems. Okay, so whenever such a property exists, then it indicates dynamic programming might be available, might be a suitable choice. Okay, so but that is not necessarily the case. Sometimes the dynamic programming can be an overkill. It's like sometimes we don't need to solve all the subproblems. And the best example is something we're gonna cover after dynamic programming chapter is done. Okay, and we will talk about greedy algorithms that we don't basically solve all the subproblems. We just choose the one that satisfies some greedy heuristics. Okay, and the second factor or ingredients is that the subproblems, they should overlap. Okay, so the space of subproblems must be like discrete or small. Like we can use a recursive algorithm to revisit the same problem repeatedly. Okay, so as a contrast, then like a sorting problem that we can solve with a divide and conquer algorithm usually is not solvable with dynamic programming, because it's an obvious fact actually, because if you given the input sequence and you cut the sequence into 2 halves, then you will get 2 brand new subproblems. Okay, so these subproblems, they seldom overlap each other, because when you sort the input sequence, it's likely that you get very random numbers. Okay, so how come can these subproblems overlap? Then I think it's quite obvious that you need to have the subproblems overlapping each other if you want to apply dynamic programming algorithm to it. All right. So now lastly, let me stop the video recording.